Thank you. Welcome. Thank you for taking the time out of your day to spend with us. My name is Joseph Idziorek. I'm a product manager on the AWS team. I specialize in non-relational databases. And what we're going to be talking about today is selecting the right application or right database for your application. So when we think about databases broadly, and there's a really good blog written last year by the CTO of Amazon, Werner Vogel, is that generally as a trend we're seeing across the industry is companies are no longer standardizing on a particular database and then, regardless of the use case, shoehorning a workload or a new application into that database. We see actually the opposite is happening, where developers are now choosing the database, they're working backwards from the use case, and they're picking the right tool for the job or the right database for the use case. And we're not only seeing, using multiple databases, but multiple databases within a single application. So we're going to talk about today is we're going to go through the common data categories and how we got to this many choices. We're going to discuss the purpose and use case for each of these models. So we're going to go through 8 different data models, talk about the use cases, the common patterns, and what's unique about these models. Each of these own particular technologies we could go into extreme depth on is, some of these data models have had, decades of, of academic research and industry practice. The purpose of today's talk is really to provide a broad overview so that you can see and understand how these different data models relate to each other and get an overview of the purpose and use cases for each of these data models. And then to have some fun, we're going to tie together some of these concepts that we're talking to in data models together with a demo. And before we leave, we're going to definitely point you to some more places where you can learn more about each individual databases or a little bit deeper topic than what we talked about today. So let's get started. So if we look broadly across the industry, we see, there's quite a few databases. I think, there's northward of, 340 different database options out there today. But they all kind of fall into these broad categories, these data categories, whether it be relational or document or key value, in-memory, graph, search, time series, and ledger. And each of these data models is built for a specific purpose. They each have their own specific use cases, and they were designed to fit where potentially another database at performance or scale at functionality, another database might not be that tool. So we're going to go through each one of these use cases or each one of these data models today and talk about what makes them unique and different. And our strategy at AWS is pretty simple. We want to make sure that we have the best purpose-built databases in each of these categories, so you as a developer never have to compromise on functionality, performance, or scale. One of the things that we see is, can you overburden a database? Absolutely, and there's a really good example of this. Back in 2004, folks may or may not know this, is that Amazon Retail was using an old guard relational database. And in December, which is a bad month for a retail company to have an outage, hit an outage, is we were unable to scale up that database any further. What we found in looking at it is that we were using the database beyond its given purpose, and it really wasn't the right fit. So a bunch of smart people went off and did a COE or a correction of error to understand what could be done here, why did it fail, what could we do differently. And in that investigation, we found that we were using a relational database as a key value store. 70% of the queries that were going to this relational database were for primary key values, right? We're using a relational database as a key value store. And that's an example of overburdening a database beyond what its intended purposes were for. As a result of this, a few smart folks went off and wrote the Dynamo paper, which was the genesis for both Cassandra and DynamoDB, which we have today. And now, this is a technology in a database that can be used for those applications that have unbounded scale for those key value lookups. So that's an example of using one type of database beyond its intended purpose. And that's really where we want to get you to, is fitting that right database for that use case, so you don't have to compromise on functionality, performance, or scale. All right, so how did we get here today? Well, if we kind of look back in time, and I'm going to throw this caveat out here, not every single database that's ever been developed is going to be represented on this slide today. I've been called out for it before, saying like, hey, I worked on this particular database in the 80s. Why don't you have it listed here? This is more for a breadth sampling of some of the more prominent and more used databases that are out there. But it's really to understand how we got to so many selections of databases. So if you think back to the late 70s and early 80s, we had some pretty large stalwart databases that emerged. And they were relational, right? Oracle DB2 and SQL Server are relational databases. And we kind of move forward to the 1990s. We got a few open source entrants into the mix, which is great with MySQL and Postgres. But you can see the data access model here for 2 decades. The predominant databases that were being used were relational. And we still see the ramifications of that today. Is actually great in many ways. Is there's so much content and books and tutorials and samples, and SQL is really the lingua franca of data. So it has been a really positive thing, especially if you're using a relational database. But if you kind of look forward to the 2000s, we see a significant increase in the variety and different types of data models that emerged. And I don't think this is a coincidence that this type of new technology came up about the same time that the cloud was emerging in the mid 2000, 2006 and beyond. And what we saw there is we saw a significant difference in the type of applications in different companies that even didn't exist pre-cloud, building and doing things that we never saw companies build and do in the 80s and 90s. If you think about some of the applications and some of the companies on this list that were born in the cloud and are building applications, global applications at scales for hundreds of millions of users, they have a vast array of use cases, and all those use cases are typically not satisfied by one single database. And thus, when you look at a trend like this, technologies don't pop up and stay around if they don't have utility, right? Each one of these databases, these data categories, fits a specific problem that help build many of these types of applications. All right, so when we talk to customers, about their database decision, their database strategy, and where they're going, there's 2 general areas of focus. One is lift and shift and moving applications to the cloud, and the other one is building net new applications. So for lift and shift, this is, the conversation is typically around, hey, I have this database that I'm running either on premises or EC2. I don't really want to be in the business of, self-managing this thing, doing high availability and, writing scripts to do backups and patching and, maintenance. That's just not my core competency. It's undifferentiated heavy lifting, and we'd rather have somebody else do that so we can spend the time building features for our application and innovating on behalf of our customers versus spending nights and weekends running a database. And in those scenarios, it's typically, folks just want to get out of the game, get out of the business of managing the database, and they just want to do a lift and shift, meaning that they just want to take, hey, I'm running, Postgres or MongoDB on premise, and I just want to get to, Aurora or Amazon Document DB, so I can get out of the business of managing that database. And one way to do that, and a really nice tool for that, is the database migration service, which makes the migration between on-premises or on EC2 databases really easy, with capabilities of being able to do change data capture and being able to replicate changes as they're happening to the application to make it reduce the amount of time that it takes to do a failover when you cut your application over to the database running in the cloud. When we talk about the second bucket, right, the folks that are building net new applications, this is a little bit different of a conversation. This conversation is about what are the requirements and what is the scale of these applications. And I think many of you, on your phone, and you do this on a regular basis, so think about the ride hailing or media streaming or social media or dating applications that you use today. Those applications are architected for millions of users, right? If you think about social media and a sporting event or New Year's, they have to be able to account for, think about New Year's in Snapchat. You have to think about how many people in every single, time zone across the world are going to take their phone out at a, relatively similar time and take a snap and want to be able to share that, right? That's an incredible amount of users and data volume. Similarly, global locality. I think every one of us, if we have a ride-sharing application that we like to use, if we get off the plane in London or Sydney or in Shanghai, that we'd be able to use that and it would have a global reach. In that we wouldn't be having latencies going halfway across the globe, but we would have a global footprint for that application, so that would be some locality to the data. I think the bar has definitely been raised and continues to get raised on performance of applications. I think if any one of us sees 300, 400, 600 milliseconds of lag in an application, we think the internet's broken, or we think that the application's broken. We refresh, we get frustrated. The bar has been raised on performance, and in industries like ad tech, where milliseconds is the difference between winning a bid and not winning a bid. And we see, performance gravitating towards microseconds. Accessing millions of requests per second. Even the game of economics has changed, where people don't want to be locked into, long-term licensing. They want to be able to pay for what they use and be able to, not pay for it when they're not using it. And of course, developers want access to things today. They don't want to wait 6 weeks for procurement of a particular resource to happen and software to install before they can innovate. They want to do this today. So if we look at companies, especially ones born in the cloud, of how they're thinking about their database strategies, and you think about Airbnb, if you've ever gone on there and looked at a property, or rented something for vacation or for travel, it looks to us like one cohesive application, right? And that's what it is. That's the whole purpose of the application, is one seamless experience, which it is. But behind the scenes, they're using multiple different purpose-built databases for each of the specific use cases, right? Search history with DynamoDB for each individual user, session state, right? For Elasticache, you don't want to be persisting session state to disk if you're going to have millions of concurrent users. They're also using relational databases for transactions. So even within one application, you have a mix of both non-relational and relational. And we actually see this in spades, right? This is a very common pattern. Similarly, if you can think of Duolingo as an application, and I know many of you have your New Year's resolution where you committed to learning a new language, so this would be a good time to fire up that Duolingo app. But you think about 300 million total users using this application. Like, thinking about architecting and choosing databases, there's no way they're going to shoehorn all of that into one single database technology. Again, they're using a solution of DynamoDB and Aurora and Elasticache, both relational and non-relational, for tracking language exercises and transactional data, and caching common words and phrases to provide that scale and that performance for their customers. So we're going to go through each of these different data models. We're going to start with relational because it's been around the longest, and we're going to talk a little bit about what's kind of unique about that data model, and what the use cases are and what customers are using it for. So we'll start off with relational, and folks are probably typically familiar with this, and the data model is stored in rows and tables, and the data is normalized. And the reason for that is one of the design points when the relational model was created was that disk was the constrained resource. And I think if we look at now, as usually typically disk is not the constrained resource, but the data model is still extremely useful. So when you have data that's normalized, and typically we talk about this as normalizing in third normal form, what you're doing is you're pushing down the consistency and the accuracy of the data model down into the database by distributing this data across tables using primary foreign keys. And it becomes very advantageous to be able to have the database enforce this data integrity. For example, in this particular schema, if I had a bunch of patients that were attached to a doctor, and I went and tried to delete a doctor that had patients, the database would enforce that and say, hey, we have this relationship, so you can't just orphan these patients without a doctor, right? And this is a good way to have, kind of stale data, is if the database doesn't enforce these types of things. In a relational model, because that relations are pushed down into the database and through primary foreign key relationships are preserved, makes it really nice to be able to do that at the database level versus the application layer. Right? And relational databases have a ton of features. They've been around for a long time. A lot of hardened cycles. They're really good for complex queries and ad hoc queries, looking for different things, piecing together, schemas that can answer a lot of different questions. Right, so for folks that are pretty familiar with this, the data model, the query model is pretty similar or pretty familiar. We're going to use SQL, where we're going to use join statements to be able to take these tables that hold the pieces of information that we want. We're going to bring them together by joining in different fields within the table. And we can do things by like counts and groups by and order by to be able to produce the result set that we need. Now I get this question asked a lot. With all these new data models, is the relational model dead? Is it, is this crufty old technology that we shouldn't be using anymore? Am I falling behind the technology curve? And like unequivocally, the answer to all those questions is no. Amazon Aurora, which is our cloud native relational database service, is still the fastest growing service in AWS history, and tens of thousands of customers using this. So not only is it not going away, it's actually accelerating. And you look at the customers on this list, they're very progressive companies that are building really large applications, and really complex applications are not only using relational technology, but increasing their usage of relational technology. So absolutely, it's not going away. I think what you're seeing is a trend of complementing relational databases with other data models, to be able to add additional use case and functionality that perhaps weren't built into applications in yesterdecades. So use cases that we see a lot of lift and shift with relational databases, especially among enterprise applications trying to get to the cloud, to get out of self-managing or perhaps long-term licenses. We see a lot of software as a service applications. There's a lot of really good features within relational databases that lend themselves really good to multi-tenancy and applications, with being able to do that within the database and enforce that within the database. And also web and mobile. Amazon.com is definitely a large user of relational databases, migrating off of Oracle to Amazon Aurora. Right. So for relational databases in AWS, we have two options. We have Amazon Aurora, which is both Postgres and MySQL compatible. And Aurora is a purpose-built cloud-native database service that was really built to leverage the economies of scale and the design points of the cloud. And we get a lot of questions about, hey, what's the difference between Amazon Aurora and RDS? Well, Werner Vogel wrote a really nice blog about this not too long ago, about a lot of the technical innovation and some of the concepts and design points that were used to develop Amazon Aurora. So I definitely invite you, to look at this blog and also other Werner's blogs. He provides some really good context on a lot of topics related to AWS. Of course, if you want to do lift and shift, if you have a MySQL or Postgres, MariaDB, SQL Server, Oracle database, to get out of the business of self-managing, we have RDS for that as well. All right, the second data model, key value. Key value is helpful because it's very self-descriptive, right? You have a key value pair, and those key value pairs are used to access the data. And we'll do this in the demo when we create a DynamoDB table. The first thing we'll do is create a partition key, or the key, and within that key we can store values, typically our documents or other types of data structures. The one really nice thing about, and this is the design point for a key value store, is that we can horizontally partition keys basically with limitless scale, right? In the example that we have here, we just have a single table, and that table can have it can have a flexible schema, and we're partitioning just by the first letter of the particular key that we chose. But we can continue to partition, right? We continue to horizontally scale and reduce that key size, almost limitless, which provides a tremendous amount of scale. And the access patterns there is because we're just using a key to look up one specific item, right? We can do consistent performance at scale with these access patterns, right? And this is why we hear a lot with DynamoDB, it's consistent performance at any scale, is because of this really, if we can make that assumption about our data model that we're going to be accessing the data with this key, you can provide single-digit millisecond latency for tables that are hundreds of gigs and terabytes in size. Right, so with the key value access pattern, we're going to be doing queries like gets and puts, be able to do scans across tables and across keys as well. And it provides a pretty nice way of being able to deal with and query this type of data store. Right, so use cases, we talked about this a little bit before. Snapchat is using DynamoDB for one of their largest storage workloads. And if you can imagine the scale at which they operate at, having something where users are contained to a single key value pair, being able to scale that virtually horizontally for as many users as they have is a really good fit for the right tool for the right job. Right, Capital One for mobile applications. Lyft is using DynamoDB for multiple data stores, including tracking GPS coordinates for their rides. If you can think about, Lyft doesn't always know when the next event is going to happen, and that a game or a concert gets out, or an event occurs in which there's going to be a spike in traffic. And having that being able to be stored in a key value store that can scale to meet those demands and those spikes is really advantageous for those types of workloads. Right, so that we have DynamoDB. A lot of really great innovations in DynamoDB in the last year. You look at the capabilities of that have been added with multi-region, multi-master, which is really a tremendous amount of functionality. Be able to write to 2 different regions and have those regions replicate over and stay in sync. New on-demand pricing, so your usage of DynamoDB, you don't have to provision any resources. You pay for individual requests, so it's truly serverless. A lot of innovation and a lot of great features and capabilities have been added over the last 2 years, and they continue to serve some of the biggest workloads on the internet today. Documents. All right, so within document databases store data in JSON-like objects, and those objects are really the first class. The JSON documents are really the first class objects of the database. And what we mean by that is it's really the design point of the database is to be able to index and query and store and retrieve those documents or collections of documents. And documents really came about, and we'll talk about this in a little bit, is it's a very natural way to store data and model data. And we think about documents, the analogy I always use to like is taking notes in class. If you can remember back in the last time you sat in a class and took notes, you kind of take it as a list. And then sometimes you tab over and you add some additional context related to a particular point. And sometimes you created, some lists separated by commas, which are kind of similar to or analogous to arrays. And that becomes the way that we think about structuring and using data. And the document model maps very naturally to that. Typically, we don't think in rows and columns in normalization. We typically think about consuming, content as a fully descriptive document. And that's really what documents are for. And they provide a really nice flexible schema, being able to index different fields within the document, and then a very expressive query language for ad hoc queries and aggregations to be able to explore and perform queries across documents, being able to do counts and sorting and aggregations. So how we got here for document databases is JSON became the de facto exchange for how we stored or JSON or objects within application, and that became really pretty standard way of storing and dealing with data in the application tier. And then it came time to persist that data that we were using the application tier to the relational tier, to a relational database, as that was typically the only database in town, or the one that was being chosen to be used. And that caused some friction, right? The JSON data model doesn't map really naturally to the relational model. So what came around to break up that friction was object relational mappers. And what these did was, what object relational mappers attempted to do was take these documents and then map them back to a relational schema. ORMs work really great until they don't. And then, it becomes a kind of an issue where you have to go back and figure out what queries are being crafted and what schema is being used in troubleshooting. And it definitely induces some friction. What really came about to solve the problem is, a whole class of document databases popped up in the mid to late 2000s that really focused on making the document the the first class object of the database, so that you could persist the documents directly to the database without having to do this translation. Some use cases, we look at user profiles. We can start off with a simple user profile with Susan, and then we can evolve this over time, right? We're not this is a case of denormalization. We're not normalizing this and shredding it out into a games table and then a bonus table and a user table. We're keeping all of the information for Susan contained within a single document. So when we retrieve something for her, it's a quick query to the database. And we can add other nested or complex data types such as arrays as well to keep track of things like promotions, right? So this is a really natural way to be able to deal and model with data. Right, we see a vast number of use cases for documents, the content management and personalization and cataloging, user profiles. And you kind of think about all these use cases, and these really have to do with structuring data in an intuitive way and in an easy way to be able to better make use of that content. What we see a lot in like cataloging is within machine learning experiments where where results are produced and there's metadata that's associated with those results, and then there's a URL to an S3 bucket, and you want to be able to ask questions like, hey, give me the top 10 experiments that produced a yield greater than 10 between these dates with this machine, or give me the number of experiments that were run on this machine over the last month, grouped by a particular time and place. So these become really interesting and very useful scenarios to be able to use the document model, and it lends itself very well to be able to answer these queries. I think what we've seen is the challenge with document databases has been, we have a lot of folks that are self-managing, and that becomes really problematic, especially at scale, because as things scale, things become more complicated. We have a lot of folks that have asked us if we could do something self-managed in this space. They become difficult to scale, and if we kind of look at some of these traditional database architectures, they were built to be able to do, they're built for exactly client servers and being able to run on premise. And the challenge at those architectures, they're fairly monolithic in nature, and that means that they scale monolithically and they also fail monolithically. So we have some customers in this space that tell us that, hey, for scaling their database, it takes them either days or even calendar weeks. And of course, being able to do with the rest of self-managing databases, security is challenging, as well as being able to configure and do backups as well. So in response to this, we built Amazon DocumentDB, which is a fast, scalable, fully managed MongoDB compatible database. We did some innovations in this service, which we'll talk about a little bit, to solve those pain points. But the purpose of this service is to provide a cloud-native database service that enables customers to run their MongoDB workloads in a fully managed database service. And what that means is, you can use Amazon DocumentDB using the same application code, same drivers, same tools as you use with MongoDB today, and get the benefits of a fully managed database service. So a few things that we looked at DocumentDB and how we'd make how we'd help make this a little bit easier for our customers to use, and we leveraged some of the design principles that we've taken from building distributed services and other database services over the years and applied them to DocumentDB. So the first thing we did was decoupled storage and compute. That becomes very advantageous because now we can scale storage and compute independently. So regardless of how large your data size is, we can add and remove instances in minutes. Is the compute instances are not a function of how much data that you have. So instead of scaling in days or weeks, you can scale within minutes. And again, regardless of how large the data size is. Similarly, we distribute the data in smaller partitions, which is advantageous for being able to do, which is really great for being able to recover if there ever becomes a failure. 10 gigabyte data partitions can be copied on a 10 gig link in seconds, which provides a much higher and resilient architecture and mean time to recovery for any failures. and increase replication 6 ways across 3 AZs. So it provides a tremendous amount of redundancy and data availability that's really unmatched. All right, so here's the architecture, which provides a distributed storage and compute, and provides a modern way for dealing with documents in the cloud. So in memory, so within memory databases, within traditional database architectures, we have a kind of a concept of a buffer cache or a buffer pool, and this is memory within the compute instances that are used to cache pages, in the instance memory, so that you can be accessed faster, right? So we don't have to page to disk all the time to get access to data, right? Well, within memory databases, that is the whole purpose of the database, is for the whole database to be in memory. Once you get rid of that having to persist to storage and disk, as many technologies and storage technologies are, is every time you kind of go down the stack, it becomes an order of magnitude slower. You can do some things that are really fast. Now, the trade-off there is you don't have the durability of that data, right? It's more ephemeral data, and usually you're persisting that somewhere else or able to reconstruct to the data that you have in your in-memory database. But for the data that you do have in there, it's lightning fast, right? Microsecond performance, as you're not reading and writing to disk. And there's some really, really great use cases here. Some of them can be very simple as gets and puts, as you're doing with caching. Databases like Redis have some really nice, complex data types that can be used to build some pretty interesting applications. We'll take a look at one of those in the demo as well, with building a leaderboard using a sorted set. Right, so the data access pattern looks something like this. This is a very simple use case, and the demo will show a little bit more complex, where we say, hey, we want to, you can think about it as a key value pair too, but it's in memory. We're going to set A to the value hello. We can come back and we can get that value, which is hello, right? That's just an example of a simple cached value. We can go and say, hey, we want to get value B. There's nothing there, right? That would be a cache miss. We can set B to be goodbye with an expiration of 5 seconds, which is nice because with caches and caching use cases, we want to expire that cache. So if there's a cache miss, we go back and retrieve the most recent data. So we can wait for that value. After 5 seconds, we can go back and it'll be null again. Use cases, pretty much the whole world runs on caching. If you think about your phone and your web browser and your local desktop or laptop, is you're caching content everywhere. And if the world wasn't using caching, it would be a very slow place. So Airbnb is using Elasticache for site-wide caching. And we see a lot of use cases in real-time bidding, real-time analytics as well, where the performance requirements are in microseconds versus milliseconds, and that's really the target use case in design point that in-memory databases were built for. So for that, we have Elasticache, which has both Redis and Memcached, which provide 2 great options, fully managed, highly scalable database services. All right, search. Search is always fun to start off with a use case. So last summer, there was this, meme or trend of these giant pool float toys, if you will, in the Seattle area, where there's these ginormous ducks or unicorns, and like you would drive by a lake and you would see this 6 foot by 6 foot rubber ducky and somebody floating on it having a good time. Now, of course, that looks pretty interesting. It looks kind of fun. And of course, we need to have one of those. However, when you go to Amazon.com or you go to your favorite place that you like to purchase things, you don't really know how to describe what you just saw. You want to purchase it. You can probably associate some adjectives or nouns to it, but you don't know for sure what it is. So, the thing that we do is we just kind of throw in there what we hope to be close enough and hope that the search comes back with relevant results. And this is really what a search engine does, right? It's really based on being able to answer questions that we don't have a precise or exact answer for. right? So if I type in pool unicorn, I'm going to get back some relevant results based on what is stored and what is there. And those are really the use cases for a full text search engine. So they work a little bit differently, and I'm going to spare the nitty gritty details than like a database like a document database or key value store or relational database. They work with inverted indexes and something that's called a stop word list, right? We don't need to index on the word in or is or it or not. And they look at being able to access data and relevancy of data using facet search and ranking and scoring based on terms and search terms to pull back documents that are most relevant for the search that went in. And you might see this in a URL in your web browser. If next time you do a search, you just kind of glance up at the URL and you'll see something like search $Q equals house, right? So imagine that we have the IMDb database that has movies that are for decades, and we just typed in we just wanted to see what movies would come back from if we just had the search term house, right? So here's what a snippet of a result set back from a search engine would look like. We would see the hits, right? 85 total, right? The max score would be 6.6. And then we would see, a nested structure of documents that contain the information for, the most relevant movies. In this case, Animal House happened to be the most relevant movie based on the search term house. And you can do a lot of different things to tweak how the search engine responds to your queries. But this is a use case in which we don't know exactly what we want, but we know some of the words that are associated with it. And this is the purpose of this data store. Right, so we see a lot of use cases for this, especially in log analytics. Adobe's a great example. If you can think the semi-structured logs from 200K API calls per second, and if you're troubleshooting and trying to understand how what's happening in those service, those API calls, you might not know the exact text you're looking for, but you might know pieces or bits of it that you want to use. Full text search like MuirWeb that we just talked about is a big use case for it. And clickstream analytics as well. You think about being able to look at what folks are clicking on and being able to do analytics across that data. So for search, we have the Amazon Elasticsearch service, which is highly scalable, highly available, and secure service for being able to do search workloads for the use cases that we talked about. All right, graph, and after this one, we'll do a quick demo. So graph, similar to documents in a document database, in graph databases, the relationships are really the first class design point of the database, and not the relationships like relational database relationships where we kind of have these foreign primary key relationships that preserve the integrity of the data. Relationships here, we're actually talking about things that actually can be queried, right? So in graph terminology, you have what is called a vertex, right? And this is the circle in the picture, but a noun, if you can think about it as a noun. And then there's edges, which can be thought of as the relationships that connect the two nouns, and those can be purchased, like things like purchased or knows or follows. And they connect the two vertices together. And the unique thing about graph database is that we can associate attributes to these edges, and we can query on those as well. Right, and they provide a means to provide, or it provides a really nice data source, some really powerful scenarios and use cases. And I think where we see, these most common is in social networking, right? Tell me the friends of my friends, or tell me people who I should also follow, or content that I also would like, or recommendations, right? We'll talk about this a little bit more. Tell me about the books that people that have bought in this book have also bought, or what else would I like on this website if I purchased these 4 things, followed this particular sport, and were friends with Bob, Allison, and Sally. There's a lot of use cases in life science and fraud detection where there's a lot of things that map very naturally in the natural world to graph models as well. Think about your network IT operations is basically a graph. My favorite use case is the books. When you think about going to, even Amazon.com, and they make recommendations for you, this is really using graph technology in the back end of being able to look at, what are associated things based on things I've already bought. right? And with the graph model, it provides a really intuitive way to be able to query these relationships. And we'll look at this particular use case in the demo. But essentially, if we say like, hey, for a given book, I want to know who else has purchased this book, and then what are the books that they've purchased, and then rank those books for me in descending order by how good they are based on the rating, right? So here we can do, this is what the query would look like, right? It looks like a builder, and it's very intuitive. If you can think about using a different data access model, a different query language to accomplish this query, I trust it would not be this clean. It would not be this intuitive to write. It would probably be many lines of codes with very complex recursive functions to be able to do some of this functionality. Again, this is a use case of trying to use another database beyond its intended purpose. Graph databases were built to answer these specific questions. Right. So for graph databases, we have Amazon Neptune, which is purpose built for the cloud, fast, reliable, and supports both Gremlin and Sparkle to be able to do some really cool things with graph data models. All right, so let's do a demo. Let's put some of these technologies to work and talk about it with some live code to make things interesting. So for this use case, let's use something that's familiar with us. We have a retail website that sells books, right? I think we've all used one of these before. And we look at this particular website or this application, we can see multiple distinct use cases, right? We have a product catalog which stores, the information in the URL pointer to the S3 bucket that contains the image for, this particular book. We have a profile, we have a shopping cart, we have a search experience, we have a bestsellers, which is really a leaderboard, and we also have recommendations, right? Books that your friends have bought. So we have 4 different use cases. Let's look into those 4 use cases and talk a little bit about some of the technology and query it a little bit, play with the data model, and talk about why we chose that for each particular use case. So the first one, let's start off with this product catalog. Now, for this experience, I chose DynamoDB. And why did I choose that data model? Well, with product catalogs, they're self-contained, right? I have a book that has either a GUID or an ISBN number, some unique identifier, right? And it has an author and some attributes and has a name and a price and a rating, and it's all self-contained. So it makes it really easy to access that data with a key value pair. So let's copy this item and create a new entry in our book. We'll make a new unique identifier. We'll call this carbs NYC for the different types of carbs that we can purchase when we're in New York. Of course, everything in New York is expensive, but it's always excellent. So we'll give it a 5 rating, and we'll create that new book. So if we go back to our website, we just added a new book to our product catalog, and we should be able to hit our cookbook tab here. We'll scroll down and see if we can find carbs New York style. There it is right there, right? But what we just did wasn't really how, if we were building this website together, this application together, we really wouldn't expect our customers to have to scroll like this to find the book that they want, right? Because perhaps they were out, at a restaurant, and one of the recipes that was used was in this cookbook, and they went home and they don't really remember exactly what they were searching for, and they said, hey, I don't know, something like NYC, I'm not sure. And they would go up and they would use the search text, or they would use the search bar to be able to look what they were trying to find without knowing the precise name, right? And what we just did that, right? We just used NYC, and we didn't quite know exactly what we were looking for, but the search engine produced the right results for us, filtering out the other things that weren't relevant. Now, you should be asking yourself, Joe, you just wrote an item to your product catalog in DynamoDB, but you just went to the search bar, which I'm using Elasticsearch for. How did that entry show up in Elasticsearch so quickly? Well, this is an example of using multiple databases together, and let me show you how I did that using DynamoDB streams. It's a really nice feature. So if you think about, especially for building applications that use multiple purpose-built databases. So we'll create a new table, and as we kind of talked about before, let's just do product NYC, and this is the partition key. So when we talked about key value pairs, this is that key that we're going to be using to be able to access our data. So we're going to say product ID, right? And we're going to create this table, and I'll show you. I've already done this for the table in the demo application, but I'll show you how I enabled streams on DynamoDB. So DynamoDB streams is like a queue. So every time that I write or update or delete an item in my table, it puts it on this queue, and then I can consume from this queue to be able to do different things with that data. So let me enable streams on my table. It's been enabled. And what's really nice is we can then couple the stream with a Lambda trigger. So I'm going to use a function that I already have, right? So every time, batch size of 1, so every time an item gets written, updated, or deleted from my product table, it's going to go onto the queue. This trigger is going to execute this Lambda function. In this case, it's going to write that data to the Elasticsearch index or update it or delete it so that I can keep my product catalog in sync with my search index. And that's a great way to use multiple databases together. All right, so those are the first 2 use cases. For the third use case, if we're building this site together, we would want to have a bestsellers list. And I think we're all kind of familiar with this. Amazon has has a list of books. So they're 20 most popular books on the website. The Billboard 100 for music, and it provides a really nice way to get the most popular and the content that is most likely for our customers to buy in the forefront and in their hands, so that they spend more money on our site. So if we're going to build a leaderboard in this particular application, what technology would we want to use? Well, if we kind of think about that query access pattern, we want to have something that is fast, right? We don't want to have something that's going to be, we're going to have to do complex queries. If you kind of think about if we're going to do this on a relational database, that query would look something like select star from, or count star from, order by, group by, and is the number of items over time increased, that query would become, increasingly slow as the number of items in our orders table increased. Instead, for this particular use case, I want to use an in-memory data store like Elasticache, and use Redis in particular because Redis has a really nice data type called a sorted set. And what the sorted set allows me to do is build a leaderboard like this, but push that functionality down into the database. So I already have a Redis cluster already created, and this is the one that we're using for the demo application, and I just want to be able to query it. So this is the query. We have books all time, and we're going to say, hey, give me back the items, the top 10 items with scores, right? We know from our website that we should only expect to see 3 entries there, right? So let's say we want to make dairy, we want to make that the most popular book. What would that look like? Well, let's imagine somebody came in and they bought a book. And let's see, they're going to buy a lot of them. They're going to buy 20 of them, and then we'll take this key and we're going to increment it, right? So we see that the value went to 126. If we go back to our book or back to our leaderboard, we can see that the sorted set in Redis has handled that increment for us, has pushed that query functionality down into the database. So then we want to produce this leaderboard. It's just this really simple query for us. Every time somebody orders, we increment the sorted set, but then the retrieval of that leaderboard is super simple. So if we go back to our website and we reload this page, right, now we can see that dairy is the top item on our list. All right, so for the next use case, so I've already built a recommendation engine. So I can say like, hey, here are the friends of, here are the books that your friends have purchased or have bought. The use case that I want to build next is every time I click on one of these individual books, I want to know what the books are that people that have purchased the book have also purchased, right? It's the use case that we had in the slides. So for that, I want to be able to use a graph database. And for me, I'm a very visual person, so it helps me to be able to visualize what my graph looks like. So for this use case, I would have something that looks like this, right? So the blue circles are vertexes, are a particular person, and we also have books as well, right? Which are the light blue books, and then orange ones are categories. So for this particular case, we can say, hey, who also has purchased this book, right? We have Justin, and then we can see the other books that he has purchased, right? And we can do the same thing. We can continue to traverse this particular graph. Now, for me, if I can see it first, it makes writing queries against it much more intuitive. So let's go take that example query that we had from the slides and run it across this data set. Now, I already have access to my Neptune database with the Gremlin console. And here's that same query that we had before, right? We're going to see who purchased this book, or we're going to do a reverse traversal, a forward traversal, and then do some filtering, some ordering, and some ranking. Right? It provides a really nice, clean way to be able to bring back the result set that we need to be able to provide that next capability of providing that recommendation engine in our application. All right. So within the application, we looked at one. To us as an end user, looks like a very clean, presented application, but behind the scenes, we're using multiple different purpose-built databases to be able to provide our end users the best possible experience so that we don't have to compromise on functionality, performance, or scale. So we use DynamoDB for our product catalog, Neptune for recommendations. We use Elasticache and Redis for our product leaderboard. We use Amazon Elasticsearch service for our product search. So that demo application that you saw today is available online. It's available. It's on GitHub. It's open source, and the team made a really nice one-click CloudFormation deployment for you, so you can deploy it into your account without too much hassle. All right, last couple data models that we're going to talk about, and then we'll get you to where you can learn learn a little bit more about each of these data models. Is time series. So time series is, really the design point for time series is really storing data around the time interval, right? So time series is a sequence of data recorded over a time interval. And you think about use cases for this and things that are typically handled in this way is weather measurements of temperature, humidity, or precipitation. Stock tickers are a really good use case. Both those are kind of considered regular data patterns. We also have irregular time series, like, hey, record the time that, somebody walked through a door at a fulfillment center, or when a particular package was picked out of a particular bin, right? Those are all events where we record this series, we record time in addition to some other information. What is special about time series databases is time is really the single primary axis of the data model, is the way in which the data is accessed, right? We make the assumption in this data model that there's always going to be a timestamp both when we're inserting data and when we're querying data. And when we do that, we can do some incredible things around performance and scale that we can't do in other databases. Yes, in other databases you can store it. Absolutely, you can store a timestamp. But the database wasn't really optimized for those axis patterns. It's probably optimized for more general purpose axis patterns than what a time series database would be optimized for. Right, so we look at a lot of use cases around application events, IoT sensors and readings, and DevOps data. And these are all cases where you want to know not just what the value is, but how did that value change over time? Was it an abrupt change? Was it a spike? Was it a slow memory leak? Did the temperature increase dramatically? At what day did it cross 80 degrees Fahrenheit? These are all different types of questions that we like to ask over time series data, and we typically like to graph it because we like to infer how we like to make judgments over how the data changed over time as well. And of course, you can do these. You can store data as a timestamp in relational or other data models. I think the challenge there is that you can quickly overburden those databases. They really weren't built for the use cases at the scale and performance that time series databases were built for. And for that, we built Amazon TimeStream, which is a new database service that is in preview today. All right, the second and last data model that we have is a ledger database. And I want you to think about ledger databases as ledger databases having two qualities. One is that they're immutable, and the second is that they're cryptographically verifiable, which means you can go back and cryptographically verify how the data has evolved over time. And those qualities are very unique to a ledger database. And you can imagine use cases in this realm for tracking anything to do with medical or hospital equipment or inventory, tracking the lineage of a car through the DMV, right? You don't want to have somebody to have the ability to delete an owner or fudge some of the data on there to make the car a little bit better than it actually was. Manufacturing, payroll. There's a lot of use cases out there that we don't want to be able to have someone have access to modifying the data, nor and also being able to go back and cryptographically verify what happened. Again, we can do this in relational databases or other models. They really weren't built for it, and I think the things that are really challenging to do there is to verify that nobody had access to the data to be able to delete or modify, whether it be the sysadmin or whoever, and really go back and be able to prove that the database had never been tampered with. There's also a lot of technologies out there, in the similar realm. You might have been thinking to yourself as, hey, this smells like blockchain. I think what there's definitely use cases for blockchain. I think with the ledger database, you can kind of think of these two things as a lot of folks use blockchain in some capacity because they really want that ledger technology, but definitely two distinct use cases. So if we think about these concepts, ledger databases have two three components. They have the journal, which stores the data, and then they provide a look at the current value and the history of how that data arrived at the current value, right? So we can think about it as journal, current, and history. And the journal, we can always, even if the database goes away, we can always replicate those states from the journal. So let's go through a use case on how this would work. So we're going to use the DMV example. Right? We have our current value, the history, and also the journal, right? So let's insert an item into, we just bought a brand new car owned by Tracy Russell. So we'll insert that value, goes into the journal, we hash it, right? And then we add that particular value to our current cars, and then we record it to the history table, right? So we have the current value, the histories table, and then the item in the journal. So let's go through and say, hey, let's say that Tracy Russell sold her car to Ronnie Nash. So what we would do there is add that item onto the journal. We would cryptographically verify it with the previous entry in the journal. We would update the owner, and then we would add another item onto our history table. Similarly, if we add a third owner, Elmer Hubbard, right, we would do the same thing. We would cryptographically verify that item onto the journal. We would update the current cars to the current owner, and then we would have another entry in our history table. Right, and for ledger database workloads, we have Amazon Quantum Ledger Database or Amazon QLDB, which is in preview today. All right, so in summary, what we really see with customers using purpose-built databases for is really working backwards from the use cases to choose the right technology, the right database for the job. And really what this equates to in the end is that they don't have to re-architect or try to do something unnatural, which yields, when you use the right tool for the job, it yields better performance scale and it has more functionality for the things that you're trying to do versus trying to build this stuff into the application code. We see that doing this is easier for people to debug, and when you partition out monolithic applications and partition those databases, they become easier to manage and create independence between teams. I think there's a really great presentation by Team Internet, which is an innovative company out of Germany that really talks about this and how database is really part of their entire technology stack. There's a lot of really good examples out there, and this is my architecture series where customers will just walk through 5 minutes of their architecture and their technology choices. There's lots of great examples of customers using multiple different databases. London Stock Exchange is a really great example. They're using Amazon Elasticache, RDS, Redshift, and Elasticsearch, and even S3, which is the largest NoSQL database nobody talks about, to build one application. So they're using multiple purpose-built technologies that each have their own purpose in that app. Right. So that's the that's the overview of these data models and some of the different services that enable you to use these data models as fully managed database services. For more information, Andy Jassy's keynotes are always great to learn about the latest and how trends in database technology. Werner Vogel's blog is great. And there's a few additional talks too, similar to this one for DAT 205 from reInvent last year and DAT 301, which is a little bit deeper dive into matching the database to the workload. So for that, build on, my friends, and appreciate the time and thank you. So we'll